Hi guys. Today's lesson is about the way that waves are going to travel, as well as talking about sound intensity and a little bit on the decibel and loudness perception that we have for sound. So to get started, right, just looking at how waves travel. So waves being mechanical waves, or sound, I'm sorry, sound being mechanical wave, it is a longitudinal wave, which we can translate into a transverse wave through the pressures, right? So remember your high density or your higher pressure versus your low density or your lower pressure. Your high density, high pressure being associated with the crest, low density, low pressure being associated with the trough. So as we look at this wave front here on the right hand side of the screen, we see different wave fronts, right? And those wave fronts that we see are associated with the compression of that longitudinal wave. So that compression being the higher density. So we see from compression to compression, we complete one full cycle, right? One full wave. Well, that compression to compression is going to be that lambda, right? We're going to see our wavelength in there. And as our sound is projected, right, the idea that it propagates in all directions really stems from how you hear sound, right? So imagine every single conversation that you've had. If sound did not travel spherically, that would mean that unless somebody was talking directly into your ear, if their mouth was pointed a different direction from your ears, you would not be able to hear them. Now we understand that if you're standing behind somebody or to the side of somebody, right? We understand how location plays into our ability to hear, but we can still hear them, right? That's the important thing to get out of this, is that recognition of somebody is in front of me looking directly at me. Here's the sound that I hear. Well, what if I'm behind them? What if I'm off to the side? It's like any teacher that stands up and talks directly to the board instead of to the class, it's harder to hear them. You still hear that individual's voice, but you don't hear it as clear, you don't hear it as quickly, you don't hear it as loudly, right? So we miss a lot of that information there. This you can also perceive if you throw a rock into some water, the way that that water is going to leave, right, in a nice smooth circle. Exact same way here, right? Except now picture air as being three-dimensional. The surface of water, you could really look at as a two-dimensional surface here. And that's what we get on this, right? We see a spherical pattern, but two-dimensional, right? It's going to travel as a circle. Now, that sound intensity, right? How we're going to perceive, right? How loud something is, how intense that sound can be, depends on how far away you are and how much energy that sound wave has in general. Our perception of sound, right, as we get further and further and further away, is that sound intensity is going to drop off, right? It's going to get lower. Makes logical sense, right? You're further away from something, you're not going to be able to hear it as well because the intensity does drop. Well, the way that intensity drops, it's an inverse square. So if you double how far away you are, it is 1/4 as intense. If you triple how far away you are, it's 1/9 as intense. Quadruple your distance, it's 1/16, right? So on and so forth. And that intensity is based on the number of sources. So like it says here, if you double the sources, you double your intensity. Picture two trumpets playing. If you want to double the intensity of those trumpets, you need to double the amount of trumpets, so you would have 4. If you have 10 people talking and you double the intensity of those conversations, right? If you had 10 people, you double that, now you're at 20 people. If you have 4 times the intensity, you're going to have 4 times the number of sources. If you have 10 times the intensity, you will have 10 times the number of sources. If you take 1 car horn versus 10 car horns, right? You're going to have 10 times the sources. The sound intensity will be a factor of 10 as well. The diagram in the bottom left really shows what happens in terms of intensity and that distance. So looking at that sphere, right, where some distance away are, we have one little area. If you double that, you have 4 area boxes to fill. Again, just making a larger sphere. If you're 3 times further away, you have 9 of those area boxes to fill. That's where we can really see how the size of that sphere is going to change. And the further away you get, right, the sphere that sound has to travel through is going to get bigger, but the sound itself doesn't change, which is why we see that lowering of intensity. And going back to the idea of the number of sources, well, let's say you increase the power of what's generating that sound, or if you increase the number of sources, it's going to be able to push back what we see with that sound, right? So really our initial sound intensity, well, if you have a lot more sources, this sphere is going to get bigger, right? Artificially bigger. So our sound is going to change based on where we are and based on the number of sources that we have. Our formula that we can use to look at sound intensity is power over area, right? So our power, again, being measured in watts. Power is energy over time, so really it's the rate that the energy is converted per area. Have a higher energy in the same amount of time, right? You have more power. More power in the same amount of area will yield a higher intensity. So power, right, we're still measured in watts. Our surface area is 4 pi r squared, and that is the area of a sphere, right? So that's your surface area of a sphere. Our distance away is still going to be measured in meters. So overall, power is measured in watts, distance measured in meters. So we're power, so watts over r squared, power over meter squared. We get watts per meter squared for our unit of intensity. Right? It's kind of an odd unit. And what we're going to see is that our values for intensity tend to be small, right? These tend to be very, very small numbers. You're going to be really hard pressed to find an intensity of 10 or an intensity of 100 or an intensity of 1000. These are usually written as very small values, right? The amount of power per unit area is small in the grand scheme of things, which is why an intensity of 1 watt per meter squared is a very, very, very intense sound. On this diagram, or on this table I should say, what we see is a relative intensity on the left-hand side with basic examples on the right, and then this column for the decibel level in the middle. We'll get to that in a moment. But again, going back to that previous point, where intensities tend to be very, very small, the threshold of hearing is 1 times 10 to the negative 12 watts per meter squared, right? That is the absolute zero, per se, of sound, for humans at least. A whisper is 1 times 10 to the negative 10. So when you're telling somebody a secret or whatever, and you need to whisper, right? That whisper not only changes the amplitude, which changes the volume, right? You change the volume, you're changing the energy that wave has. If you change the energy, you're changing the intensity, right? Because that power has changed as well. So we really see how everything ties together here. A volume change is an amplitude change. That amplitude change represents a change in energy of the wave. That energy is part of power, which is part of the intensity. So your quiet whisper has a low volume, which we associate to a low power, which is then a low intensity, 1 times 10 to the negative 10th. A single mosquito that's buzzing, for example, 1 times 10 to the negative 8th. Compare that to a typical conversation, 1 times 10 to the negative 7th. Even as we get into a lawnmower, right? You all know how loud a lawnmower is. You all know how loud a car horn is. Look at those numbers. I mean, there's still less than 1. 1 times 10 to the negative first, that is 0.1 watts per meter squared. That is a car horn at a meter away, which is about 3 feet. A jet airplane, which is substantially larger, you see that it's 1,000 times larger in terms of the intensity from the threshold of pain, is 1 times 10 to the negative third, right? That's 1,000 is a jet airplane, right? That is exceptionally loud. Very, very intense, very damaging to your ears. As you get past that threshold of pain, remember, this is where you can start getting temporary to permanent hearing loss based on how strong that sound is. So the decibel scale that was on that previous slide, what the decibel scale is, it's relative to our threshold of hearing, which is why for decibels there is no official unit. We just always abbreviate it as dB to represent decibels, but it doesn't have a unit like meters or meters per second or watts per second squared, right? There's no unit to it because it's all relative to how intense that sound wave is compared to the threshold of hearing. Picture something as quiet as you can. There's still a little bit of sound there. And decibels is just, okay, how much louder is this sound in comparison to that sound? Right, so 0 decibels would be at our threshold of average hearing, and that's going to be true for any frequency because you have to have a certain amount of intensity in order to be able to hear something, even if you're at 1,000 hertz, for example. 1,000 hertz, if that sound is not intense enough, you still can't hear it. We have to get that intensity into our threshold before we can actually record that. What we see here is how we can get from decibels to intensity to our perception of loudness, right? How we perceive that volume based on the decibels and the intensity that we see. The chart that's present is showing what happens as things get louder. So if our loudness gets twice as loud, our human perception of that amplitude, right, the energy that that wave contains, if we perceive something as being twice as loud, the decibel increases plus 10, the intensity is multiplied by a factor of 10. In order for something to be twice as loud, if we put this back in perspective of the number of sound producing sources, if you have, I don't know, let's go with, one person talking, and we want to have a perceived loudness of 2 times. If we want to know how many people that is, we have to look at the intensity, right? The intensity is 10 times more, we would have 10 times more people. Bring that into a restaurant. If you're having a conversation with somebody around you, right, there's 2 more people. Well, for every 10 people, that would be twice as loud then. Which is why restaurants get really loud really fast. You start looking at the amount of people that are talking, and that sound intensity really goes up, which means that loudness goes up as well. If you walk into a restaurant and you're the only person there, it's not going to be very loud. If you walk into a place that has 100 people there that are talking, it's going to be 4 times louder than just a normal conversation that you're having. And that perception of 4 times is a lot, right? That is a much, much, much louder sound. Our decibel scales that we see here, right? For every time we double our loudness, we get 10 more decibels. Every time our intensity increases by a factor of 10, we increase by 10 decibels as well. And again, that decibel scale is all relative. Let's say you have something measured at 60 decibels, and you want to know how much louder it is when it's measured at 80 decibels. Well, there from 60 to 80, we have a relative increase of 20 decibels. So that sound would be 4 times louder and 100 times as intense. If we flip this, so notice the scale now has switched, now the sounds are getting quieter. Same idea happens here. The rate that things get quieter is the inverse of the way that things get louder. If we have a 30 decibel decrease, let's say you have something measured at 50 decibels and now we're down at 20. We have a reduction in 30 decibels, so it would be minus 30. That sound would be 1/1000th as intense and would be 1/8 as loud. And the same perception of how it's going to be less loud and less intense, we could do the same scenario. Let's say something is at 120 decibels, we go down to 90. We still see a change in 30 decibels there. That sound would be 1/8 as loud and 1/1000th as intense. Obviously at 90 decibels, that's still a very loud, very intense sound in the grand scheme of things, but you compare it to what it started at. And we can go back to the front here, exact same idea. Something that goes from 50 to 90 decibels, for example, right? If we use that plus 40, right? 50 to 90, that's plus 40, 16 times louder, 10,000 times as intense. What if we go from 10 to 50? Same increase in our decibels, right? Still plus 40. That sound was 16 times louder and 10,000 times more intense as well. Remember, because intensity is all relative, you can compare sounds even if you know what their decibel levels are. You can find the difference between them to be able to figure out intensity and loudness. So that's the way that we look at our decibel scale, our intensity, and our perception of loudness. Again, just really going through here, making sure that you can see that as it travels spherically, right? We get further away, we get less intense. We can calculate our intensity through power over 4 pi r squared, so power over the area of the sphere. And then we can translate that into decibels, intensity, and our perception of loudness.